Last lesson, we spoke about how X-rays were produced, and that's nothing to do with imaging the human body. That's just production of X-rays, slamming fast-moving electrons into a target, and as the electrons decelerate within the target, X-rays will be produced. What we're going to do today is turn our attention to the human body, though, and we're going to ask, how do those X-rays actually interact with human tissues so that we actually produce an image of the human body? If you want to have a look at this in the textbook while we go along, on the PDF, it's 27.2. Okay, so we need to talk about the beam intensity, because pretty much what's going to happen is that a whole load of X-rays are going to leave the window on the X-ray machine. And if every single one of those X-rays were to pass through the patient and arrive on the detector on the other side of the patient, then we would just get a uniform black image in which every pixel on the detector had detected some X-rays, and the entire image would have detected the same amount of X-rays, and the entire image would just be a uniform shade of black. But on the screen right now is a typical X-ray, in that much of the screen has fogged away and been turned from a white color to a dark gray color, but some bits haven't. You can see on the image on the screen right now the outline of the arm bone and some ribs and the sternum, and that's because X-rays have not made it to the detector at that point. What has happened is that the intensity of the beam has varied by different amounts depending on which path it took through the body. Any beams of X-rays that pass through the soft tissue arrived with a large intensity on the detector, but any paths of the X-rays that pass through bone arrived with a much lower intensity. And what the detector basically does is color code the intensity of the arriving beam. So any bits that arrive in high intensity get colored towards black, and any bits that arrive with low intensity get colored towards white. And we interpret that as being that something dense and absorbent reduced the beam intensity. So if this is the principle for how an X-ray image is formed by a detector, we need to investigate beam intensity. We need to look at how the intensity, that's the power per meter squared of the X-rays, reduces as it passes through the human body. Okay, so we've already met this idea in the waves topic. We met in the waves topic that a point source would radiate energy uniformly in all directions, and that energy would spread out from the source on the surface of an ever-expanding sphere. And therefore the intensity, which is the power per unit area, would go down as the area went up. And because the radiation is spreading from a point source uniformly in all directions, it's covering the surface of a sphere, and the area of a sphere is 4 pi r squared. So the area will be going up with r squared, r being the distance from the point source, and therefore the intensity will be going down as r squared. So that should be familiar to you from the waves topic. But important to remember that when we met this inverse squared relationship in the waves topic, we were talking about the radiation traveling through a vacuum that didn't absorb it. What we need to do in this topic now is to take account of the fact that while the radiation is trying to spread out from the point source inside the X-ray machine on the surface of a sphere as a 1 over r squared relationship, while it's trying to do that, it's not going to manage it, because we're going to place a human body in its path, and the human body is not a vacuum, and it is going to absorb some of the intensity of the beam, and therefore that relationship, that 1 over r squared relationship, will not be true. for any of the X-rays that pass through the human body. So we need to modify our relationship. We are not going to have a relationship in which the intensity reduces as the square of the radius. Okay, so that's a much nastier looking equation. We haven't really looked at exponentials yet, although we did do at GCSE when we met radioactive decay and half-lives. So you might remember about exponential decay. You will also at some point study exponential curves e to the x and e to the minus x in your maths A level, if you're doing one of those. I don't know if you've done exponential curves yet. Yeah, you have. Okay, so hopefully that's familiar to you, but let's just unpick the equation. What we're saying is that I0 is the intensity that is arriving on the surface of the material, in this case, human body tissue. So if you were to place a detector not behind the human body, but on the surface of the human body, I0 would be the intensity that's measured. But then what happens is that we've got this factor e to the minus mu x, which is going to be less than 1 because it's e to the minus mu x. That's going to be a decimal that's less than 1. So you can think of it as when x is 0, e to the 0 is 1, anything to the 0 is 1. So at a distance into the human body of 0 centimeters, 0 meters, that e term will be 1, and so we'll have I0. But then as x increases, e to the minus mu x will get closer and closer and closer to 0. And so for every millimeter that we pass into the human body, that term, that e term, is just going to reduce the I0 so that by the time it's come out of the back of, say, a 3 centimeter wide bone, then we'd have e to the minus mu times 0.03, and whatever that comes out at, that's going to make the intensity of the X-rays that entered the bone be smaller when it leaves the bone. Mu is called the linear attenuation coefficient. I don't think you need to remember that term, but you do need to remember what it represents. It represents the absorbency of the human tissue. So if the human tissue, like bone, is very, very good at absorbing X-rays, then mu is going to be a large number. And that e to the minus x term is going to fall away to 0 very quickly indeed. And so it's going to have a very large impact on I0. On the other hand, a human tissue like skin or muscle will have a very low mu, a very low linear attenuation coefficient. And that means that the e to the minus x term will never be very significant, even if x is quite large. And it can never be that large for a human body. So that means that the intensity of the X-ray beam coming out of the other side of the tissue will not be that much different to the intensity that went in. And that will result in a blacker area on the image as opposed to a whiter area. If you're wondering how big mu is and how we know, well, how do you think we find out what the linear attenuation coefficient is for human tissue? We make use of that phrase, donated to science, and there are people who, when they die, leave their body to science, and some of those bodies are used for medical students to explore as part of their studies. That's kind of like the famous use of left to science. But actually, some of those human tissues have been placed on X-ray machines, and we've different thicknesses of them, and we've shone the X-ray beam through, and we've measured the intensity on the other side, and it's been a direct measurement of mu for every tissue in the human body. So you can look up what the linear attenuation coefficient is for every tissue in the human body, and you know, it's out there on Google. You can do that after the lesson, maybe. Okay, so that's the basic principle, that the intensity of the beam will be lower at the back of the patient than the front of the patient. And you might have to do calculations using that formula, and there are some at the end. But what I'd like you to focus on for the remainder of today's lesson is, why does the beam attenuate? How is it that human tissue manages to reduce the intensity of the X-ray beam? What are the atoms in the human tissue doing physically to the photons of the X-ray beam, so that not all of those photons make it to the other side of the patient? Okay, so there are four main mechanisms, physical mechanisms, by which X-ray photons are absorbed or otherwise scattered by the human body. So the four mechanisms are scattering, your friend the photoelectric effect, which you know all about, something new called the Compton Effect, and pair production, which is what we just talked about with E equals mc squared in the particle physics topic. So we're now going to take each one of those four in turn, and we're just going to make sure you understand the basic principle of each one. In the exam, when you finally get to it, it is common in this topic to maybe ask you to do a calculation involving the intensity formula that I just showed you, but also to then answer maybe a 3 or 4 mark question to explain what one of these four is, maybe with a diagram. Or they might even ask you a 5 or 6 mark question in which you are invited to compare 2, 3, or all 4 of these to each other. So it is important that you understand how each one works, and that you don't muddle each of them up with each other. It's also important that you don't muddle any of these 4 up with the Bremsstrahlung or the excited states of the electrons that we met in X-ray production last lesson. Some of these feel like they're very similar to what we did on Monday, but they are not. Okay, let's go through each one in turn. Okay, simple scattering is exactly what you think it is. It is where X-rays, as photons, basically just bounce off the atoms in the human body. They don't interact with those atoms. They don't do anything to those atoms. They just behave like elastic snooker balls bouncing off the atoms or the electrons in the atoms. The reason that they don't do any interaction with those atoms is because simple scattering will take place with the low energy X-rays. These X-rays don't have enough energy to do anything to the electrons in the atoms. The electrons are sitting in their little energy wells, being held in place by the positive attraction of their nucleus, and they would require a certain amount of energy to liberate them from their atoms, or even to move them up an energy shell within their atoms. And the low energy X-rays simply don't have enough energy to do that. Instead, the photons simply bounce off or scatter. What this means is that the X-rays do come out of the patient. They're not absorbed, but they don't come out in the same direction they were heading in. And the direction they were heading in was towards the detector. So they are going to come out the patient, but they're going to fly off and hit the wall somewhere. They're not going to hit the detector, and they're not going to get detected. And that's why the beam intensity goes down, because some of the X-rays, they end up somewhere, but they don't end up where you were expecting them to. However, there should be a little objection coming through in your understanding of this right now. Does anybody want to unmute yourself and object to anything I just said? You're all very shy. Okay. Well, what you should be objecting to is that there are no low energy X-rays in the patient, because if we produced the X-ray machine properly, we will have hardened the beam and we will have removed all of the lower energy X-rays before they got anywhere near the patient. So in actual fact, although you are expected to know about simple scattering, it's more important that you can make the point to the examiner, if ever invited to do so, that actually simple scattering is not relevant in radiography, because we should have hardened the beam and there shouldn't be any low energy X-rays in the patient. Okay, let's have a little look at the second mechanism. So when we taught you about the photoelectric effect in the earlier topic, the photon topic, we focused on it being a process that liberated electrons from a piece of zinc. But actually, that was just an example, because zinc happens to behave very nicely and demonstrate the photoelectric effect very clearly with a UV lamp in a school laboratory setting, and so we focus on zinc. But I wouldn't want you to go away thinking for a moment that the photoelectric effect is just a metallic thing. It is the case that any photon can be absorbed by any electron and can release that electron from wherever it is. The electron in a metal surface will have a work function, but an electron in one of your tissues will have a work function as well. This is the minimum energy required to release it. And as long as we provide a photon with enough energy, E equals HF, so that HF is larger than the work function, then the electron will be absorbed, the photon will be absorbed into the electron, and the electron will be removed from the material. Now, X-ray photons have quite a lot of energy. The work function of the electrons in your body often have quite a lot of energy, and actually they match quite well. And the photoelectric effect is one mechanism in which the human body, the tissues of the human body, will remove X-ray photons from the beam. Remember, the intensity is all about how many photons there are. And so what we're going to be doing every single time the photoelectric effect takes place is that a photon will be removed from the beam and the intensity of the beam will go down. And of course, if the photon isn't making it to the detector, it can't get detected. And therefore, the detector will detect a reduced beam intensity. So hopefully not very much learning to think about with the photoelectric effect, because you already know all about it. It's just widening your appreciation that it's an effect that takes place not just for electrons in metal surfaces, but for electrons anywhere in any material. Okay, this is a new one. Okay, it's called the Compton Effect, after the person who first came up with it. Okay, so what Compton did was to treat the photon as a particle that has momentum and can undergo collisions in which not energy is exchanged so much, but momentum is exchanged. Now, in the classical idea that a photon is massless, and momentum is mass times velocity, then you may well be objecting to the notion that a photon has momentum. But that's a simplistic view of the photon and also momentum. The photon has energy, and Einstein taught us that E equals mc squared, and that in some sense the photon has mass energy rather than just energy or just mass. We didn't study it because we didn't do relativity, but Einstein also reinvented the concept of momentum for us, and relativistically, massless particles can have an improved version of momentum, relativistic momentum. So what the Compton effect does is take relativity into account, and it asks what would happen if the momentum of a photon was able to be transferred to an electron in one of the tissue of a human body. So what will happen is that, a little bit like simple scattering, the photon is going to ricochet. It's going to bounce off in a different direction. Unlike simple scattering, where the photon will exit the body still as an X-ray photon, in the Compton effect, the photon will exchange momentum and most likely also energy, and therefore the photon will lose energy. And by E equals hf, if E has gone down, F's going to go down, and it's probably not going to be an X-ray photon anymore. However, even if it is an X-ray photon, it's probably traveling in a different direction. And so it's not going to hit the detector anyway, because it probably isn't traveling in the direction of the detector anymore. But even if it is traveling in that direction, it probably isn't an X-ray photon anymore. And the detector is detecting X-ray photons rather than photons in general. And so probably the X-ray detector is not going to pick up a non-X-ray photon. It might, but it's probably not going to get to the detector anyway. The Compton effect is very similar to simple scattering, and it is really easy to muddle them up. Just try to remember that in simple scattering, the X-ray photon bounces off, but it's still an X-ray photon, still with the same amount of momentum and energy that it had before, just traveling in a different direction. And the human tissue was probably not affected by it. Whereas in the Compton effect, the photon will change direction, and it probably will change energy as well, so that it probably isn't an X-ray photon anymore. And it will also have an effect on the human body. It probably just ionized one of the patient's atoms. It probably knocked an electron out. And if that electron was responsible for a chemical bond in a protein that the human body was relying on inside that cell, then it's just caused a little bit of damage to the atom, and thereby the tissue that the atom was in. So this is an ionizing effect, and it is going to cause damage to the patient's tissues. Okay, that was the Compton effect. Pair production is the funkiest of the ones that we're talking about today. Let me move that out of the way. Okay, so if you imagine that there is an electron sitting in the human tissue, orbiting its atom, minding its own business, and then what might happen is that an X-ray photon enters the tissue, and it might be that the X-ray photon was just going to carry on through and not interact with the electron at all. But then we have to remember what we learned from particle physics, that it is possible for energy to turn into matter and matter to turn into energy. And actually, there are no rules in quantum mechanics to prevent this from happening at any time. And although the probability may be low, it is non-zero that the X-ray photon might spontaneously turn itself into a particle-antiparticle pair. And in actual fact, if you read enough about quantum mechanics, you will read that we actually believe that the vacuum of space is a seething mass of virtual particles as photons from stars stream through the vacuum of space and continuously turn themselves into particle-antiparticle pairs, which then promptly, immediately annihilate with each other and turn themselves back into photons again. And so quantum mechanically, if you could zoom in and see the vacuum of space at a subatomic level, you'd see it as this quantum foam of frothing particles popping into and out of existence all of the time. And that in actual fact, quantum mechanically, there's no such thing as a vacuum, not even close. Now that's a little aside, but what we're talking about here is what happens if it pops into existence as a electron-positron pair while it's inside your tissues. Well, what might happen then is that run it again for you. The positron might end up annihilating with an electron in one of your tissues. And this has just removed an electron from existence. But when the positron was created, an electron was created with it, and that just escaped. So what it looks like is that the photon comes in and your electron leaves. But it's not your electron that leaves. It was a brand shiny new electron that had just been created moments before. Your electron got annihilated by its positron friend. When the annihilation takes place, a new pair of photons will be produced. It's often a pair in order to conserve momentum. You don't need to worry about why it's a pair. The point is that that pair of photons will very likely not be traveling in the same direction that the original single photon was traveling in. And therefore, the pair of photons that were produced by the positron annihilating with your electron, neither one of those photons will hit the detector. And in fact, neither one of them will be X-ray photons either, because there will be one photon's worth of energy is now being shared between two photons. And so, again, a little like the Compton effect, they're not X-ray photons anymore, and they're not traveling in the same direction anymore. For both reasons, the detector will not detect the photon. It's not there anymore. And again, this reduces the beam intensity. So for all four reasons, just to give you the big picture overview, there is a detector on the other side of the human body waiting for photons. And it doesn't get them because either the photon scattered off in a random direction, or the photon was absorbed by an electron, or the photon interacted with an electron and ended up traveling in a different direction with a different amount of energy, or the photon produced a particle-antiparticle pair, which resulted in an annihilation event and the creation of more photons, but not X-ray photons and not ones that are arriving at the detector. For any of these four reasons, the detector detected fewer photons than it was supposed to. And so it's able to paint us a picture that this pixel on the detector detected a lot of X-ray photons. Let's color that in black. This other pixel on the detector detected fewer X-ray photons. Let's color that in white. And so we can make up this black and white image of grayscales, basically, of where lots of photons got through versus where very few photons got through. And just like the image that's in the background of this slide, the tissues that are very good at doing any of those four mechanisms, such as bone, where there are a lot of atoms, it's a dense material. The materials are often heavier elements on the periodic table. They have lots of electrons, lots of scope for any of those four mechanisms being in play. So your denser materials end up coded in white because not that many photons made it through to the other side. And also, just to be clear, three of those four mechanisms do result in ionization of the human tissues, which is bad. It produces damage. Everything that I've just said to you takes you up to, the state of X-ray technology up to about the year, I don't know, 2000, something like that. But around about that time, we switched from film X-rays to digital X-rays. And film X-rays, I'm sure you've seen in films, if nothing else, is where you take a large piece of plastic that has been soaked in a chemical that is responsive to light. And when the X-ray photons fell on this plastic sheet, they would produce a chemical reaction in the chemicals, and this would chemically change the color from whites to blacks. And the more photons that arrived, the more the chemical reaction would occur, fueled by the photons, and the darker and darker and darker it would get. So up until about 20 years ago, the production of an image using X-rays was very much an analog technology. When we moved to digital X-ray imaging, which effectively uses the same kind of technologies as the charge coupled device, the CCD that's in your phone camera, but a bigger version of it. When we moved to that, it became clear that we could produce exceptionally good X-rays, and that it was now the human body's tissues that were letting us down. That bone has a very, very high linear attenuation coefficient, and all the other tissues in the human body have a very, very low attenuation coefficient, and they're all very similar to each other and low, which means that although X-rays are excellent for telling the difference between bone and not bone, they weren't very good at telling the difference between any soft tissues. And so we decided that we would improve human tissues so that we could image those as well. So this comes under the heading of contrast media. What we would like to do is to be able to contrast the difference between muscle and skin, or your lungs and the muscle around your heart, or something like that. So is it possible to tell the difference between things that are not bone? And it turns out, yes, it is. All we need to do is help the human body to modify its mu. We need to take tissues that have a low absorption coefficient and manually inflate that coefficient. We need to do something to the human body to make it better at absorbing X-rays. Now, we can't actually do anything to the human tissues to make them better at absorbing X-rays, but we can fill them with a material artificially that is good at absorbing X-rays. So what we choose to do, if you want to image non-broken bones, anything that's not a broken bone, is that we invite the patient to allow us to flood their tissues with an external material that is very, very good at absorbing X-rays, that has a high linear attenuation coefficient. So you can't easily do this all the time for all tissues. For instance, we wouldn't want to be doing this to your brain. That would be bad, to put foreign materials in your brain. But there are some areas of the body where it is completely possible to do this. So for instance, imagine your digestive tract. It is basically a tube running from the top of your body to the bottom of your body, and what's inside the tube is technically outside your body. The opening of the tube is at one end of you, and the other opening of the tube is at the other end of you, and we can pour stuff down that tube and it'll go in one end and come out the other end, and it doesn't get inside your body. But while it's there, it will absorb X-rays. So we can ask patients to swallow, drink this. It's quite nasty. It's called barium meal. You can drink this liquid, and it'll wash down into your stomach and then your intestines. And as it makes its way through your body, it will show up on the X-ray really, really well. Or if we're only interested in your large intestine, we can invite the patient to allow us to push it up from the other end of the digestive tract in something known as an enema. I'll leave you to think about that. Or if we're imaging the lungs, we can ask the patient to inhale a gas that, again, doesn't get inside the human body. It goes in and out of the lungs. And while it's in the lungs, we can image the body. So we might ask the patient to inhale the gas, hold their breath for a moment, take the X-ray, and then they can exhale it again. For some tissues in the body as well, it's possible to inject a high contrast media into the blood. Although my understanding of it, that it's preferred not to do that if it can be avoided, but it is a technique that is used. Okay, so what does that look like when we do it? Well, if you've swallowed, or I guess had an enema in that case, something with a high contrast medium, is that the small intestine? Might be. Then it will show up like that on the X-ray. So that's soft tissue. That shouldn't be showing up on an X-ray, and yet it does. We're not really imaging the soft tissue, I guess. We're imaging the barium that the patient has taken into their body. But it allows us to have a little look to see if, for instance, the intestine has become twisted, which might cut off a little bit of blood supply to that part of the intestine, or it might trap a little bit of feces in that part of the intestine. And if that isn't rectified, then that part would become necrotic and can lead to blood poisoning, not to mention have a long-term problem on your digestive system. So it's a well-used, well-tried and tested diagnostic technique. So it all comes under the heading of contrast media. It's this notion of putting an artificial substance inside the human body that is good at absorbing X-rays so that we can image that and thereby deduce where human tissues are.